Right, this is a quick look at nuclear fission and how it works. This is what happens inside a nuclear power station. So hopefully you know a little bit about nuclear power stations from the energy unit, but we're going to look in a bit more detail about what happens inside the power station. So this is an atom of uranium, and it's uranium-235, the isotope used. So there's 235 things in its nucleus, 92 of which happen to be protons. And if I was to fire a neutron at it, it turns it into uranium-236. Now, uranium-236 is incredibly unstable, and it splits. So as soon as the neutron gets absorbed, it becomes incredibly unstable, and then as it splits, you'll notice, hopefully, that there's a few things given off. So watch closely. So there's that yellow circle that emanates from it, and that's meant to show all the energy that's given off. So this process gives off a lot of energy. But there's also, if you look closely, these smaller things given off as well. And they're neutrons. Sometimes 2, sometimes 3 neutrons given off. But if you think about this process, it takes a neutron to start it, but then when it splits, neutrons are given off. So those neutrons could go on to cause other things to split or to fission. And that's what would be referred to as a chain reaction. I can aim my gun here. So let's bring in some nuclei. So if I fire a neutron at this, it'll become uranium-236, then it will split, natural things to do for uranium-236, and then when it splits, it will release some neutrons. Now if those neutrons go on to be absorbed by other uranium-235 atoms, then they'll split as well. If it gave off 3 neutrons, and they all got absorbed, then you'd go from having 1 splitting to 3 splitting, to 9 splitting. So it gets out of hand very quickly. Let's have a look. And away it goes. Now that's completely uncontrolled. And that's what's known as a chain reaction. One thing causes the next, causes the next, causes the next. So it's an uncontrolled chain reaction. The rate of the reaction just keeps getting bigger and bigger and bigger, and that's what would happen in a nuclear bomb or nuclear explosion. So how do we slow that down? Remember, the nuclear bomb came before the nuclear power station. So we want to slow this process down. And, well, actually, before we do go to that, I'll mention this. This is it took them some time, actually, before they could keep it going. So if you don't have enough, it fizzles out pretty quickly. Oh, we didn't get them all. We nearly did, I suppose. So I could have it a little bit less. And it actually was a long, interesting story behind how long it took to get the nuclear bomb up and working. And you know, there was more than one side in the war working on the nuclear bomb, and then the atomic bomb was dropped on Hiroshima and then Nagasaki, and it was it changed the way the world thought about weapons. And so for a long time after those bombs were dropped, people were very worried about nuclear war, and it went on and on and on. And these nuclear weapons, though, scientists were thinking, well, if we could just harness that energy and release it more slowly and gradually, then we could use it to do what every other power station does, and just heat water. So, this is a nuclear power station. So a nuclear power station does exactly that. It's a nuclear bomb where the reaction is slowed down. And it does it with these. These blue things are control rods. So these are the uranium atoms. They be all together in uranium fuel rods, and the fuel rods are placed into the reactor. So if I take the control rods out completely, fire a neutron to start off the reaction, then you'll see pretty quickly it'll spread across. You can see, I mean, the total energy produced will end up here, but you can see the power is getting very high. And that would create an incredible temperature, which would create a huge pressure, and you'd have an explosion in the power station, and that would be a nuclear bomb being set off in the power station if there was no control rod. So obviously very, very dangerous. So I'll reset the nuclei, and then I'll just put the control rods in. So if we fire the neutrons, it will die out pretty quick. So these blue control rods are there to absorb neutrons. And they absorb the neutron. So when a neutron is given off, instead of going to hit a uranium atom, it will be absorbed. Now there's a bit more to it. This seems to show that as soon as a neutron gets emitted, it gets immediately absorbed by a uranium atom. And it's not that easy, otherwise it wouldn't have taken that long to make an atomic bomb. But for GCSE, that's all we need to think about. The neutrons that are given off can cause further fission. So what you need to do is you need to find a point where you absorb the right amount and let the right amount pass through. See, it died straight away there, that reaction. Here we go, so I can kind of fiddle around with it. And really, you could find this site yourself. You want to try and keep the power nice and low. So it's just a steady release of power to heat the water gradually, but you don't want it dying out either. You don't want to have to restart it. Nuclear power station actually has a very long startup time, so it's always left on. Okay, so gradually see the neutrons going across from one fuel rod to the next. Now there's not really someone messing around with this, but if you wanted an immediate shutdown, you could just drop them straight in if there was a problem, and you could see actually that doesn't shut it down straight away, doesn't it? The reaction keeps going on, but it's there for a control measure. So these blue rods are called control rods, typically made out of boron. And the control rods are they absorb neutrons, and their job is to control the rate of the fission reaction, and to make sure that not too much energy is released at once. Otherwise, the pressure will get too high. You'll have an explosion. Okay, so that is nuclear fission and how it occurs. So, if you were asked to draw a diagram of nuclear fission, all you would need to do is show a neutron being fired at a circle, which you could, if you called it uranium, great, but it doesn't only happen with uranium. The other fuel that's typically used in power stations is plutonium. So we'd call that the nuclear fuel. And then you'd probably just draw a couple of arrows off to show what it splits into. So these two products that you can see, those two, I'd just draw the two arrows to show that it splits off into those two. And then you could draw two other little arrows showing neutrons being given off. Now because it's 2 or 3 neutrons, it's always easier to just do the 2 neutron diagram, and then that would be a fission diagram. Now if you were asked in the exam to draw a chain reaction, then you can notice that actually if I just take this down, I mean the chances of one causing the next one in this, pretty slim. Oh my word. Oh, anyway, it's nearly there, but all you'd have to do is imagine this diagram continuing. So if you have that going off to your 2 nuclear products there, and then you've got your 2 neutrons, you'd have to continue the diagram till those 2 neutrons hit another nuclear fuel, your uranium, and then show them splitting into 2 products, what is called daughter nuclei, and 2 neutrons as well. So that would be the diagram for nuclear fission, and the diagram for the chain reaction. Never seen them ask you to draw a nuclear reactor, but I have seen them ask you what the point of the nuclear reactor is. It produces heat to heat water, which spins a turbine, which turns a generator to give you electricity. But commonly they'll ask about the control rods. What is the job of a control rod? It absorbs neutrons, so it can control the rate of the nuclear reaction. Okay, so that is nuclear fission, and it's what takes place in a nuclear power station. Now there's a very similar word, which is nuclear fusion. And nuclear fusion takes place inside a star. And they're very different, but they're spelt very similarly. So fission, F-I-S-S-I-O-N, or fusion is F-U-S-I-O-N. So make sure you don't do a mix between the two. You have to get the right amount of S's in. It's 1 S for fusion, and it's 2 S's for fission. And nuclear fission is what occurs in a nuclear power station. Okay, I hope that was helpful. Thank you very much.